So today I'm going to talk about unittest.mock and kind of walk everybody through like how it works internally. So unittest.mock is a standard library in Python, and it provides a bunch of utilities. So as a bit of background, let's say you've got some source code that you want to write tests for. It does a bunch of stuff like it makes network requests, or it accesses the file system. So this is just an example of some code that is not even really production quality code. It's just, I wanted to give an example for the slides of like something that has side effects and that you want to write some tests for. The idea of this example is that you want to just download, you're going to download some files. It makes some, you want to check if the remote file that you're going to download will fit on your disk using, so we're going to use shoot.disk_usage and just request.head to get the content length header from the remote file system. Obviously there's some edge cases where this clearly doesn't work. This is just an example of some code you want to test, and we're going to use the unittest.mock library to make that happen. So there's a bit of terminology. The two things we're going to go over here are patching and mocking. So patching is like replacing an object with a fake lookalike during tests. In Python, this is done at runtime using duck typing. In other languages, you have to like statically compile and like use codegen to create mock, or like, well, so you got mocks and you got patching. They're kind of two very intermingled concepts. You usually use patching to replace real attributes with mocks, where mocks are the fake objects that have no side effects. So like for the example that we're going to talk about, you don't want to make network requests, you don't want to like access the file system during your tests, because those have problems at test time for reasons like if you have if you make network requests or you access the file system, you're introducing flakiness or extra state into your tests. Your tests are not hermetic. They rely on, like, if you want your tests to have a, like for every set of inputs, you have a consistent set of outputs, and by introducing extra variables to that, like network requests or file system stuff, you're creating a situation where the test doesn't run consistently on your machine. Say maybe your disk is full or the network is down or something, and it may not run consistently with other developers. The test works on my machine is not a really good excuse. By using mocking and patching, your tests will run faster. Like obviously you're not making network requests that would be slow. You're reducing flakiness, setup time. Sometimes you want to mock databases. Databases need migrations. You don't want to run those every time you set up your test suite. For the sake of unit tests, you want to only be testing a small little chunk of logic in each single test. And by having that test do its setup or tear down or make network requests, you're introducing more things in that test scope that you don't want to test. Like maybe you want to test like what happens when the network request gives a 500 error. How do you handle that? But you don't want to have to test all the other logic of the function. You can just test one thing. And then by not accessing real resources, you can also increase parallelization of your tests. Again, you don't need to spin up a database if you're doing mocking or patching. You can just, each test can talk to its fake little database, and it can be parallelized. I'm not going to go into much further detail on like the actual practices of writing tests. The purpose of this talk is to go into how the standard library implements the mocking and patching utilities that it provides. So the goal of this talk is to just go over the internals of the library. We're going to slowly build up an implementation using our own little code snippets to match what the standard library is doing. And then we're going to, the goal is to learn how the standard library is doing the mocking and the patching. But the implementation that I'm going to come up with, the snippets, is going to match the what and the how, but not really the like exact implementation that the standard library is doing. The standard library is quite messy. There's a lot of like 20 years of baggage in the module that really doesn't matter to understanding how it's working. There's actually a lot of dead code in there. The standard library it's not a very well written library. I mean, good intents from the developers, but it's got a lot of history with it. And I'm going to shy away from showing the actual code snippets of the library because, again, they're messy and it's just too confusing. The code snippets I'll be showing are really just concise, manually created things that show the concepts rather than the real implementation. And as a bit of a background, I'm Bryce Beagle. I work as a software engineer in California. I deal with developer infrastructure, so I'm kind of responsible for back-end things. A lot of other teams at the company I work on deal with the actual services and the production code, and I help them with their tools. I help do language version, package version, migrations, linting, static analysis tools, build systems, stuff like that. And that's just where I get a lot of the experience with like the internals of libraries. Okay, so we're going to start with doing things manually. Just the most primitive example of a patching. So we have, let me get the laser pointer working. All right, I've got this test here. We want it to call this space available function that I was showing before with some parameters, and we don't want it to make network requests or file system access. So we can just take the actual modules that the test is going to be using. So here, over here, we got requests. Well, in the snippet from the previous slide, we was using requests and shootel. We import them into our test scope, and we can just use the Python access semantics and just replace what's in the module at runtime. So we can just overwrite shootils.diskUsage, which are with our fake mock disk usage over here, and the same with the request.head function. And then when we run our test, it's going to run these functions inside of the actual code instead of running the real requests. Obviously, there's some problems with this because previously we were just setting it, and then when this test finishes, it stays set. Like the next test that run will still have this overwritten. Like it's not scoped. And that's a huge problem. We want it to unset with every test. And so we can just do a little something simple here where we overwrite it, keep the track of the original version of the function, and then when the test is finished, we put it back. Pretty simple, but there's some flaws with that. When like let's say that the function we're testing has an unexpected exception, like probably indicates a bug in the code that the tests are going to like catch, but we want to still clean up our patching when that occurs. And so we can just wrap that in a try finally statement so that when the test runs, maybe has an internal exception, it still gets cleaned up. We still put it back into its original state. We can do a little bit of work to hide the boilerplate around this. So now here I've created this patcher class. This kind of mimics what the standard library is doing. That initializes with some object we want to patch, the attribute we want to patch on it, and the value we want to set it to. And so then we make a little patcher like helper function that instantiates an instance of the patcher class. And we can see the example over here. We pass in the module the attribute we want to set on the module and the value we want to set it to. So we're setting the attribute disk usage to that mock function that we created just a second ago. And then we call these start and stop or start and finish, I should say, functions to do our setup and teardown. There's a bit of sacrifice that we have to make with autocompletion here. Previously, we were doing shootil.diskUsage or request.head. Now we have to use string lookup here just so that getAttr and setAttr work properly. But that's just what is expected and how this works with the standard library as well. We can go further and reduce even more boilerplate by changing our start and finish functions to enter and exit functions so that we can turn our patching into context managers. So the patch function here returns an instance of the patcher object that we made here. And then when the with statement uses it, it first calls the enter function, returns the object of the context manager, and then when the function scope falls through because it's the context manager, it calls the exit function. And so now we no longer have to remember to call the cleanup code for each patching. It just happens implicitly when the with statement falls through. And the beauty of context managers is that they handle exceptions automatically. So even if an exception is raised in this space available function, the context manager will still call exit. And this exception info parameters here with context managers allows you to access that exception data For the purpose of what we're doing here, we can just ignore it. We want to do the exact same cleanup whether or not an exception was raised in the internal function. And so this cleans up a bit. We can just use a context manager and ignore or not have to worry about like every single test rewrite that uses patching to do that cleanup. We can go a bit further and to replace that context manager with a decorator that then uses the context manager. So we can do @patch, provide our parameters, and then when this, so the way decorators work is that they call the function that it wraps around. So like this returns a callable. The function is then passed to the callable. So like the call function takes func, and then when that function, the wrap function is called, it actually does with self and does the context manager that we just did on the previous slide. So now all this is all wrapped, all the logic we had from the very first example with like the setup and teardown is all kind of embedded in a single line per patch, where we just are replacing our the real attribute on shoot_disusage with our mock one, and it handles the cleanup for us. It's really clean and really elegant, and it's quite nice to use. But however, there's some caveats and gotchas here that really trip people up when using the patching library. The fundamental problem is that we are patching attributes. Let's go back. We're patching attributes on the module, and so if the actual code that we're testing against gets those attributes in a different way, then the patching we're doing is patching it in the wrong spot. So in this case, over here, if the code is importing shootil and doing shootil.disusage, it will have a different reference to this code here, where if it imports disusage from shootil. And so this variable here, this disusage one and this shootil one are different things. And so if we look at the patching here, if I patch shootil.disusage and I print the variables of disusage and shootil.disusage, we can see that only like disk usage from shootil, or shootil.disusage was patched with the mock disusage, but the one we imported from shootil is not patched. They now refer to like different functions. And so we get around this by just being cognizant of where the patching needs to be performed. So again, if we're importing from shootil in our example code, we need to patch shootil's.disusage. If we're importing disk usage into the namespace of the code that's using it, we need to patch that namespace and change the disk usage inside of it. So it's a bit, we've kind of lost the ability to do black box testing. We have to do white box testing. We have to know how the code is implemented in order to test it, which is not great, but this is just how it works with the mocking and patching system that Python provides. And this is a really common gotcha that trips other developers up. It's like, why isn't my patching working? I'm patching it, I'm doing the patch function, and you have to take a step back and look at, oh, okay, it's because this variable was imported this specific way. And this also causes problems during refactoring where like you move a function or you change how something's imported, and then the patching no longer works. This can be pretty frustrating to debug, but that's how it goes. One more thing we can do as a convenience, instead of like importing the module into our test scope and then patching an attribute on it, we can use package util.resolve name, just take the whole thing as a string, split it on the final period, and then import the left side, patch the attribute on the right side, and this allows you to just use one single string to do the patching. This is what the standard library does internally. There's a bit more complexity to the standard library where it does a lazy import of the actual module that you're patching, but this implementation here kind of just does it immediately when you do the patching. But I'm not going to go through that logic. Just kind of wanted to show what the string-based approach is doing. So again, the standard library still provides the other method to do the patching on the actual symbol. It's just kind of, they put a function in the namespace of the other function. It's kind of like just, like you have def patch, and then they do patch.object equals and then another function, because like you can put methods inside of, or you can put functions inside of functions, which is kind of weird. It's not like a nested function, but it's an attribute on the function object. And so now we have the two primary decorators of the patching library, just at patch and patch.object. One takes a string, one takes a module, or sorry, one takes an object. The advantage of the second one is that you can do things that the first one can't do. If you pass a class or a class instance, you can patch attributes on the class, but if you use the first approach, you can only patch modules. So this is why it's called patch.object, because you're patching an object. But modules are objects, so you can patch them that way as well. Okay, so the other half of the story is the mocking. Here in the previous examples, we took our fake, like we manually created these mock functions, and then we put those in the patching utility. But this is a lot of work to do for every single function or every single attribute to make like a copy of it manually. And so the standard library also provides a mock utility library to like automatically generate these fake objects. Okay, we're gonna work to implement that. Let's start simple. We just have a mock class. It takes some return value, and when you call it, it returns that return value. So, step back a bit. Okay, so here we can patch util.thisUsage to take a mock that returns some fake data. So this function particularly returns a tuple of 3 integers. We don't, for the scope of our test, we only care about the third one, which is like the amount of space on the disk that is in that path. So this path is on some partition. That partition has 10,000 bytes remaining on it. And so by providing the return value, when this, so we take this mock, we put it in the disk usage place. Like in the util namespace, we assign disk usage to this mock. This mock then gets called and returns the value we provided when we construct it. So let's see here. Let's add another feature to this. So instead of returning a value, maybe we want it to raise an exception internally. It's like we want to test that we're handling our exceptions properly. And so the patching utility provides a side effect, or sorry, the mocking utility provides a side effect attribute that instead of returning the value, if the side effect is set, you can raise it instead. The actual standard library handles, or like, you can pass either an instance of a class or a class type, or sorry, an instance of an exception or an exception type, and then it kind of does some logic to infer if you need to raise it or instantiate and then raise it, but I'm not showing that here. And also ignore the usefulness of this test. We're kind of testing the patching and mocking itself. We like say this function returns or raises a permission error, and then we're catching the permission error. But obviously, a real test would be testing the handling of the exception that's raised internally. But this is just to show an example. Okay, we could also make, well, the standard library also makes side effect do some more things. If we set it to a callable, like a function or a method or anything that implements that underscore call magic method, we can make it call the function instead and then return the value. So here's just a very trivial thing. I just kind of re-implemented the previous logic by making a function that just takes anything and returns the values that we care about. Obviously, you could provide much more complex logic in here. So like each time it could like store some state, each time it's called it returns a different value, or you could make it actually look at the input parameters and like parse them, do something with it, and return a value based on how the function's called in the first place, all while still doing the mocking and patching. But yeah, the real implementation is being patched over the top. Okay. So it's the side effect attribute also supports being an iterable. If you provide just like a list or a tuple or anything that's iterable, when it is invoked, each time it's invoked, it'll return the next item in the iterable. So like you kind of like take your iterable in, you store it as the iter object, and so that iter object keeps the state. Each time it's called, it goes to the next object with next down here. And then when that's done iterating, it's finished. Let's see here. And I'm not saying this is a good API. We kind of made use of side effect for like multiple different things. We got like just raising exceptions. We've got calling it. We've got returning multiple attributes like we use the iterator function. And I will admit it's very gross that we're kind of overloading this single attribute for multiple use cases, and then still have our return value down here for another use case. But that's what the standard library does. It's kind of weird. Okay, see another important feature of Python's mocks is just accessing arbitrary attributes. We can implement getAtter on our mock type, and then whenever we access anything on our mock instance, we make it return another mock. And this allows us to make the mock that we provide to the actual logic just do nothing, and do nothing as deep as it wants to go. And this is a way that you can just, you can tell the code, just ignore everything this attribute's doing. We do not, or this field is doing. We don't care anything about it. You can get fake data back as long as you want. Just ignore it. Note that we're using getAtter and not getAttribute. GetAttribute is called whenever the namespace, you're trying to get an attribute off the object. So even if it's there, getAttribute is called. But getAtter is called only when the object doesn't exist in the namespace. It can't find it the normal way, so then it follows back to getAtter. And then it's okay, this field doesn't exist on the object. Let's create one and then return it. The standard library also provides a tool called Magic Mock. It's basically the mock thing, but it also implements a bunch of default values for the magic methods. So there's 20 of them. So it's when it initializes, it just goes through each of the magic methods, puts them in the class, and then you can use this to just get free tools on the magic mock. This is the standard thing that the patching library, the @patch decorator, if you don't set a value for it, it will return a magic mock for you. And then you can just iterate over it or cast it to an int. And this just allows you to say, all right, I'm ignoring even more functionality. I don't care. And the example of this is maybe you're making an API request and then you iterate over the list result it gives you. You could just make that by using a magic mock, it's going to return something that's iterable but has no data and then just does nothing with it. And so that just happens automatically. You don't have to do all that implementation for it. Okay, got 2 minutes left. We'll skip that. Okay. So what if we don't want all the attributes? Maybe we want it to be a bit more nuanced. Only let the mocking tool return data for the things that are on the real type. And you can provide a spec type where it uses dir at runtime to figure out all the attributes that exist on the object. And so if it's not in the dir, it raises an attribute error. But if it is in the dir, it creates a fake mock. So here we have an example where this class example has atter and do thing. And so atter works, a do thing works, you can call it. And it still returns a mock object, but A, B, C, D, E, F doesn't exist on the example, and so the mock won't create a fake version of it. But one thing to note here is that if you can use dir with both classes and instances, if you provide the class, it won't have the things that are put on the class at runtime. So self.foobar here doesn't exist if you call dir on the class, but if you call dir on an instance of the class, you can do foobar, and then it will exist. So there's 2 ways you can approach the specking. Another feature, I think this is the last one I've got to talk about, is that when you can keep track of the calls that these mocks, we have these callable mocks, you can keep track internally of when and how they're called by just storing the args on the call list. So we take args and quargs, put them in this call type here, and then we can later use our list of calls every time this fake function was called to do some assertions. So in this example, we mock shoe_disUsage, we set the return values, we run our function, and then we can assert that the disUsage was called with the file path and the request.head function was called with the URL because we store those data in each mock's call list. And then that's it. Any questions? And I'll put that slide back up because it's a long one.
Thank you, Bryce, for demystifying unit testing for me and hopefully for a lot of you. And we have 2 questions from the general public. So first question is, what strategy do you suggest to avoid mocks not being deactivated and contaminating results of other tests.
Can you explain what you mean by
Yeah.
deactivated? Yeah.
You can plug the mock inside the test, and then you need to unplug it, right? But sometimes it happens in PyTest, for example. It happened to me that a mock was actually being active also in other tests, because maybe the code was not removing it.
Yeah. So yeah, I think the problem that occurs there if you are mocking some like module object and you're running tests in parallel. If you're running tests serially, let's go all the way back. The context manager for the patcher should be cleaning it up when it's done. Like it should be unpatching it. There shouldn't be a situation where like if you're running tests serially that it doesn't clean it up after the end. That would only occur if you're running tests in parallel and you're mocking the same module. Like you're running tests in parallel, one test has mocked the module, the other test tries to use the module. And that's kind of just something you got to be cognizant of when writing these. With the approach that the standard library takes, you can't really avoid that. You can try to write your tests in a way, or your implementation in a way that you're always, test and implementation in a way that you're always mocking like objects as opposed to modules. So like the return value of the function you mock. But yeah, it is kind of tricky and I don't have a great solution for it.
Okay, thank you. And second and last questions, which is a bit maybe vague, is how to unit test an LLM-based app? I don't know if somebody wants to clarify this question.
Hello.
Yeah.
So basically, for standard machine learning, you have a reference data set, you have some scores, and you want to call the model and check on the unit test if the scores match, for example. But
Yep.
NLM, it's non-deterministic, and each time you have some other variations. But it's a challenge for me to have some. If I do a change to the code, I want to make sure that the code doesn't break and have the same output from the LLM. Is there any trick or way to unit test that and have some? I know other talks called about evolve, for example, as a package, but I'm not sure if there's something to add there.
So what you want to think about there is when you're writing unit tests, you want to test units of code. So like so the way you approach this is you are making a call to a function that then calls an LLM and that returns data. And so you can, if you mock the final return result of that, you can have a test for just like how you, like say you have data you've parsed out of the LLM's result. You can like write a test for using the data, and you can write a separate test for parsing the data, and you can like the one that's related to usage of the result, that can be completely mocked away, and it can be agnostic of how the actual LLM is returning data, like what format it's doing, what like result it's doing, and then you can have another test that kind of you can either take an approach of more an integration style where it actually calls out to the LLM, it's going to be slower, you're not actually patching it, or you can make an approach where you just kind of write a whole bunch of test cases like, okay, these are all the different ways the LLM has ever returned data, let's make sure we can parse every single one of these results, and that you're not calling the LLM, you're kind of testing the parsing logic as opposed to the LLM invocation logic. But you're still going to always want some integration tests or some end-to-end tests, like you got the classical test pyramid where you have as many unit tests as you can possibly have, and then a smaller number of like integration tests, and then an even smaller number of end-to-end tests. And so you can't really replace the end-to-end test with just pure unit tests. Yeah.
All right, we have one last question.
Hello, hello. To answer the previous one, or you could use VCR could solve that problem as well. I have a question regarding databases. You mentioned that sometimes you would prefer to mock database responses as well. Did you really have a situation in your past where it was really hard to parallelize something as a result of the database, or the database was making your tests flaky in some sense? Because I personally have never encountered that situation as long as your database internal structure is separated per test per instance.
I can't think of a situation where database tests have caused flakiness, but the idea with patching a database is that you can have multiple different kinds of tests in your test suite. You can have, like if your function makes a call to the database, does some query, and then it returns data back, you want to, same with the LLM question, you want to like make sure you can handle the result from the database properly and write a whole bunch of test suites for that. But the scope of handling the data doesn't necessarily require you testing the database itself. You can have a different set of things that like spin up a database, make some queries against it, make sure you get the data out. And you can have a different set of tests that like just assume the database gave you the result it wanted and test the logic with that. And so you can like, in that case, you can patch the database return result so that you're not actually calling the database for those, you're testing the logic you care about for the scope of those tests.
Thank you.
Yeah.
All right, thank you, Bryce. Let's give him a last round of applause. And feel free to catch him outside.